We then apply the Cauchy-Schwartz inequality, which says for two column vectors A and B and their scalar product, we get this here. So this is also written with the norm A and the AB scalar product like this. This is equivalent to this. So we obtain equality if both vectors are collinear. So if B is equals K times A with some scalar K. And this tells us how to solve the maximization task. We can now apply the Cauchy-Schwartz if we set A equals to x of n and B equals to hm. So we replace here A by x of n here and B by hm here. So we're getting this, and we get the equality, the maximum, if we set h of m equals to k times x of n, where we can choose the factor as k equals to 1. Since we have this inequality for all time steps n of our convolution, we choose n where the row vector x has the maximum energy. This is where we capture the entire non-zero waveform of our signal x of n with our filter. Since our filter vector hm contains the time reverse impulse response, we obtain the entire time reverse signal as our matched filter, assuming our signal to detect is located between 0 and L.